Hello, today I am going to demonstrate Faraday's law of magnetic induction. So here I have a setup. There's a galvanometer here. It's a very sensitive ammeter, and to that there are three solenoids connected. Each one, they have different number of turns. However, their cross section, as you can see, is the same. So the first thing that I'm going to do is that I'm going to insert a bar magnet as shown here through these coils and see what's going to happen. You can see there's a deflection. Now here you have a large number of turns. Look at the deflection. The deflection is greater than the previous one. In this case you have the largest number of turns, so I'm going to expect the largest deflection across the galvanometer. Here you can see the largest deflection there. So that means for this case you can see the largest current flowing through the galvanometer. So Faraday said that when the magnetic flux is changing across a conductor, there's an induced electric current proportional to that change in the magnetic flux flowing through that conductor. So that's what you see here. When I insert the bar magnet across the conductor, the magnetic flux is changing. It's changing with time. As a result, there's an induced electric current flowing through the circuit. Now, when there's no relative motion between the magnet and the conductor, you can see there's no deflection, because Faraday said it's the change in the magnetic flux that generates the induced electric current. Not simply the magnetic flux, but there has to be a change in the magnetic flux. Now in this particular case, you can see there's no change in magnetic flux. As a result, there's no induced electric current flowing through the system. As soon as I insert or remove the magnet, there's a change in the flux. As a result, there's an induced electric current. Okay. Now you can see when I insert the north pole, look at the deflection, the direction of the deflection. Now when I remove the north pole, the direction changes. So that means the flow of the induced electric current changes. If I insert the south pole, you can see it's completely opposite to the north pole. So this direction of the change for the electric current is basically due to Lenz's law. Lenz's law gives you this direction of the induced electric current. Basically, Lenz's law tells you that the change in the magnetic field is opposed by the induced electric current or the induced electromagnetic force, EMF, what we call it. Okay, so that's what Lenz's law talks about. So I have my next demonstration is on Lenz's law, and I'm explaining that, but this setup is mainly to explain Faraday's law of magnetic induction. So I hope you learn some very interesting physics through these demonstrations. I'm hoping to catch you again in another demonstration based on physics. Thank you.